Hey everyone, welcome back to another lesson in MCV4U. Today we'll be looking at vector and parametric equations of lines in R² or 2 space. Again, remember when we look at vector equations of a line in 2 space, the equation of a line in 2 space again is equal to y is equal to mx plus b. And so to write this, again we need 2 points. Again, and those 2 points will be our slope and our slope to our y-intercept or our slope and our y-intercept. And so here, again, to find the vector equation of a line, we need, again, either 2 points or, again, 1 point and the direction vector. Okay, so again, note here, again, in either situation, a direction vector m is necessary. So again, a direction vector is represented as a non-zero vector, again, vector m, which is AB, again, parallel, again, or collinear to the given line, L, which determines the direction of the line. Again, here, note that, again, the direction vector, M has its tail at the origin and head at the point AB. Again, here, every line has an infinite number of direction vectors, t, again, times the direction vector m, and here where t is an element of real numbers, but t cannot be equal to 0. So here t, again, is a scalar multiple. So example number 1 says, again, to state a direction vector for the line that passes through points C, 3, 4, and D, 7, 2. So here you see that, again, our direction vector M is equal to vector C, D, again, C is the tail, and D is the head. So here we're given, again, our change in x and our change in y. Again, here we see that we have, for x, we have 7 minus 3, which represents, again, our change in y, or change in x, and we have 2 minus 4, which gives us our change in y. So here, our direction vector m will be equal to 4 and negative 2. And so here we can also divide this by 2, which will be equal to 2 and negative 1. And so here for b, it says it has a slope of negative 5 over 3. So here we know that, again, our slope is equal to negative 5 over 3 which is equal to, again, negative change in y over change in x. Again, we can also represent this again as y2 minus y1 over x2 minus x1, which is also equal to delta y over delta x. Okay, and again here at the top, if we write it as negative delta y over delta x, here we see again that the negative will multiply to both the top and to the bottom. So here we can write the direction vector m in two ways based on what we just looked at. Again, it can be written as 3 and negative 5, or as negative 3 and 5. Okay, and for C here, again, it says a vertical line passing through the point negative 5, negative 6, and 5. So here, if we look at, if we draw this on a graph, and so here again, if we have our vertical line, and we see here, if we have this as, for example, again, negative 6 and 4, and this being, again, negative 6 and 5. Again, what we see here is that our slope will be equal again to delta y over delta x. Again, because it's a vertical line, our change in y here is 1, but our change in x here is going to be 0. So when we look at our direction vector, vector m, it'll be 0 and 1. So that would just be equal to j, which is a unit vector in the y direction. So here it's important to see that, again, for a horizontal line in the direction vector, for a horizontal line, the direction vector would be 1 and 0. So for the vertical line, again, it's 0 and 1. For the horizontal line, it would be 1 and 0. And again, that means here our direction vector would be equal to I. So it's a unit vector in the x direction. Again, because here, again, delta y over delta x is equal to 0 over 1. So here, again, this would be a unit vector in the x direction. Okay, so example number 2 says a line passes through the point 2, 5 and has a direction vector m, which is equal to negative 4, 0. Sketch the line and direction vector m. Okay, so here again, a line passes through point 2 and 5. So here we just write here 1, 2, 1, 2, 3, 4, 5. So here we have, again, the point 2, 5, and our line passes through that. Okay, and here we have a direction vector. Again, m, which is at -4 and 1. So here we'll go -1, 2, 3, 4, and 1. So again, starts from the origin and goes here. And so that will be our direction vector m. And then we also have our line that passes through point 2,5. For B here, it says a line passing through A 4, -5, and B 3, -7. Sketch this line and direction vector m. And so here again we have 4, so we'll put this on the grid. So 1, 2, 3, 4, and -1, 2, 3, 4, 5, 6, 7. So again, here we see that A is at 4 and -5. We see that B is at 3 and -7. So again, this is A and this is B. And we have our line here. And so here we can calculate again for our delta y and our delta x. So this is our delta y over our delta x. And so here our direction vector m will be equal to 1, 2. And so here again our x is 1 and our y is 2. And so here again our direction vector m will be equal to 1, 2. Okay, so here when writing the vector equation of a line, in general, again, to write the vector equation of a line, again, we have vector r, again, where, again, here xy is the position vector of any general point on the line. And we have x, o, and yo, again, is the position vector of a particular point on the line. And we have ab, again, is the direction vector of the line. And then here t is the scalar multiple. Again, so again, it's written as the vector r is equal to x, o, yo plus t, and then the point a, b. Okay, so example number 3 here says, and state the vector equation of the line passing through point 4, 1. Okay, so here we see that if we look at our direction vector m, and that's equal to delta x and delta y, which is again our q minus p. So here that would be 7 minus 4 and -5 minus 1, which is equal to 3 and -6. Here we can divide both values by 3, which will give us 1 and -2. So remember again, here the p is our tail and our q is our head. So here if we write the vector equation of a line, vector r is equal to 4, 1. So again, a specific position vector of a particular point on the line, plus t, again, which is our scalar multiple, and then by AB, which is the direction vector of the line. So here that would be 1 and -2. And here, again, t is an element of real numbers. Okay, and so here each value of the scalar t in the vector equation, vector r is equal to xo, yo, plus, again, the scalar multiple t in the point AB, t being an element of real numbers, corresponds to a point on the line, the scalar is called the parameter of the line. So here for the vector equation found in example 3, if we let t be any real number, for example, t is equal to 3, then here we can sub that in. And here we'll get vector r is equal to 4, 1 plus 3 times 1 and negative 2. So that's equal to 4, 1 plus 3, negative 6, which will give us 7 and negative 5. Okay, so then here if we look at, again, now parametric equations of a line in 2 space, again, we can write equations of lines in another form which emphasizes how each coordinate of a point is related to the parameter t. Again, our general form that we wrote it as is, again, xy is equal to xo, yo, plus the scalar multiple, and then times coordinate ab. In component form, again, we can write it here as xy is equal to, again, xo plus ta and yo plus tb. And so here, again, this is the x and this is the y. And so then isolating for each component, again, we see that, again, x is equal to xo plus ta, and y is equal to yo plus tb, where, again, t is an element of real numbers. Okay, so example number 4 here then tells us to find the vector and parametric equations of the line through point P17 and the direction vector m is equal to 3, negative 7. Okay, so here we have, again, our point, which is at 1 and 7. And here we have our direction vector m, which is at 3 and negative 7. And so here we see that if we write our equation, so here if we write our equation, our vector equation, again, that would be equal to 1, 7, which is our point, plus our scalar multiple t, and our direction vector, which is 3 and negative 7. So that would be our vector equation. And then our parametric equation, then we split up into our x and y components. So here for x, we would have x is equal so let's just write this as x component. And so for that, again, we would have x is equal to 1 plus 3t. And then for our y component, it would be y is equal to 7 plus 7 plus negative 7t, so 7 minus 7t. And so that's our parametric equations. Okay, and so part B here, for example 4, says to the points 3, negative 5, and 5, negative 5, 21 lie on the line that we found above. So here, again, here, remember these. Again, 3 is x, negative 5 is y, negative 5 is x, 21 is y. So here we will sub it into our equations. So here we get 3 is equal, so in terms of the x component, we get 3 is equal to 1 plus 3t. Here we get 2 is equal to 3t, and 2 over 3 is equal to t. For our y component, we get negative 5 is equal to 7 minus 7t. We have negative 12 is equal to negative 7t. Here we get 12 over 7 is equal to t. And here what we notice is that the t values for x and y are not the same. And so here a note is that if the point lies on the line, then a constant value for the parameter can be found. So in this situation, again, therefore we can see that 3 and negative 5, again, point is not on the line. Okay, and then so again, we have to look at the other point, which is negative 5 and 21. So here we will sub that in. So here we have negative 5 is equal to 1 plus 3t. Negative 6 is equal to 3t. And here we see that t is equal to negative 2. And for our y component, again, we have 21 is equal to 7 minus 7t. 14 is equal to negative 7t. T is equal to negative 2. And so here we see that those are equal. And so again, here we see that negative 5 and 21 lies on the line. Okay, and then part C says find the intercept and the slope of the line, then write the equation of the line in the form y is equal to mx plus b. So here we have, again, m, our slope, which is equal to our direction vector, which is also equal, again, to our delta x and our delta y, which is equal to delta y over delta x. And so here we see that if we look at our direction vector, we see that that is equal to 3 and negative 7. Again, 3 represents, again, our delta x, and our negative 7 represents our delta y. And so here that means that our slope is equal to negative 7 over 3. So here now we have y is equal to negative 7 over 3 x plus b. I want to find the y-intercept as well. We will sub in a point such as 1 and 7. And so here if we sub in the point 1, 7, get 7 is equal to negative 7 over 3x. Or sorry, the x will be 1 here, plus b. And so 7 plus 7 over 3 is equal to b. And so 28 over 3 is equal to b. And so therefore, our equation is y is equal to negative 7 over 3x plus 28 over 3. Okay, so here example 5 says determine a vector equation for the line that is perpendicular to r. So to vector r is equal to 4, 1 plus s negative 3, 2, and s is an element of real numbers, and passes through the point P, 6, 5. So here this represents our line 1, And so again here, line 1 is perpendicular to line 2. And so here, slopes are negative reciprocals here. And so here that means again that M1 is equal to negative 1 over M2. Here we see that the direction vector, again for M1, is equal to negative 3 and 2. Again, that means our slope for M1 is equal to 2 over negative 3, which represents delta y over delta x. And so here, that means that our direction vector for M2 will be equal to 2, 3. And so M2 is equal to 3 over 2, which is, again, represents our delta y over our delta x. And so here we see that line 2, again, will be represented as vector r, and then our point, which is at 6, 5, plus t 2, 3. And again, here t is an element of real numbers. So remember again, 6, 5 represents our point. T again is our parameter. And 2, 3 is the direction vector. And so here, again, that's our vector equation. If we want it as a parametric equation, then again, we split it up into the components. And so here we have for x is equal to 6 plus 2t, and y is equal to 5 plus 3t. And so here again, a vector equation of a line has an unusual feature, since any vector parallel to the line will do as a direction vector, and any point of the line can serve as a particular point required in the equation. Again, two vector equations may look entirely different, yet still represent the same line. Again, it's important then to determine whether or not the two different vector equations in fact represent two different lines or the same line. Okay, so here, again, are the lines represented by the following vector equations coincident, which means, again, the same line. And so line 1 is 3, 4 plus s2, negative 1. S is an element of real numbers. Line 2 is negative 9, 10 plus t, negative 6, 3. T is an element of real numbers. Okay, so what we have to really do here is, again, we have to determine, or we need to check if the two lines have the same direction vector and if the points provided in each line verify the other equation. Okay, we'll see that through our parametric equations. Okay, so the first thing we want to do is, again, we want to look at our direction vectors. So this is, again, I guess our first step here, again, look at direction vectors. Again, if we look at our direction vectors for, again, slope 1 and slope 2, again, for our first direction vector, again, it is at 2, -1. For our second direction vector, it's at -6 and 3. If we divide both of those by -3, we'll get 2 and -1. And so here, the first thing you can see is that since the direction vector of M1 is equal to the direction vector of M2, line 1 is coincident, or at least parallel to, again, line 2. So to confirm that, again, we need to verify the points. And so to do that, again, here on, if we look at our point, again, from line 1, again, that's 3, 4. And so here we're going to check that on line 2. And so again, -9 and 10 plus t, -6 and 3, that's line 2. Here we have x is equal to -9 minus 6t, and y is equal to 10 plus 3t. And so here, if we sub those in, we get 3 is equal to -9 minus, again, 6t. 12 is equal to -6t. -2 is equal to t. 4 is equal to 10 plus 3t. -6 is equal to 3t. And therefore, -2 is equal to t. And so here we see that point 1, again, which is 3, 4, lies on line 2. And so now we just have to check the last thing here. So our point on line 2, again, which was -9 and 10. Again, we need to check on line 1 to see, again, if it lies there as well. So here we have line 1, which was 3, 4 plus s 2 and -1. And so here for our parametric equations, we have x equal to 3 plus 2s, and we have y is equal to 4 minus s. So here, if we sub that in, -9 is equal to 3 plus 2s, -12 is equal to 2s, -6 is equal to s. And then also here we have 10 is equal to 4 minus s. S is equal, 6 is equal to -s. -6 is equal to s. And so here we see again that point 2, -9 and 10 lies on line 2. So here we see that after all of that, that therefore line 1 and line 2 are coincident, which are the same line.